Alright guys, in this video we're talking about the measures of variability. First of all, let's take a look at this example here. Let me pull out the marker. To order food at a McDonald's restaurant, one must choose from multiple lines, while at the Wendy's restaurant, one enters a single line. The following data represent the wait time in minutes in the line for a simple random sample of 30 customers. Of course, the 30 here is the sample size, and is equal to 30. At each restaurant during the lunchtime hour. For each example, answer the following. Part A, what was the mean wait time? Part B, draw a histogram of each restaurant's wait time. So let's take a look at part A. So based on what we learned in the previous video, we know that since this is a sample, of course, we're looking for the sample mean. So the sample mean x bar is going to be equal to the sum of all x values divided by the little n. So basically, if you want to find out the sample mean, you just need to add all of the numbers in the data set together and divide by 30. And the same thing for the wait time at McDonald's. I wouldn't do the calculation here. You can do it by yourself, and the answer is given here. So once again, x bar is equal to sum of xi over n. So that's how you calculate the sample mean. So based on the result given here, we know that the mean wait time in each line is 1.39 minutes. So which means after the calculation, we have that both those two data sets got the same mean, right? They got the same mean. Part B, histograms. Now let's take a look at the histogram. The first one up here is a histogram for the wait time at Wendy's. Now we can tell that this histogram starts at 0, ends at 4.0. Right? Now let's take a look at the second histogram over here. This histogram starts at 0, ends at 5.0. Now I will say that this one, the second one here, is more spread out. But based on what we got in part A, they got the exactly same mean, which means mean is not the same. Mean is not the measure of variability, because if mean is a measure of variability, if they got the same mean, they should have the same dispersion. They should have the same spread out. But in this case, the second graph over here is more spread out than the first one, so the mean is not the measure of variability. That's what I'm trying to tell you. Mean is not the measure of variability. But what is a measure of variability? That's what we're going to talk about in this video later. So first of all, let's take a look at a new definition called the range. So the range R of a variable is the difference between the largest data value and the smallest data value. That is, the range capital R is equal to largest data value minus the smallest data value. So basically, if you want to find the range of data set, you just need to find the largest number and then find the smallest number. The difference between them will give you the range. Now let's take a look at the example here. We got the following data set, which is the same data set we saw in the previous video, and we want to find the range. So based on the definition, the range is equal to the largest number, which is 43, and minus the smallest number, which is 5. So 43 minus 5 is 38 minutes. That's how we find the range. And then after that, let's take a look at a new definition. It's called the population standard deviation. Since we have the word population over here, of course, the population standard deviation is a parameter. Okay. Now let's take a look at the definition. The population standard deviation of a variable is a square root of the sum of square deviations about the population mean divided by the number of observations in the population capital N. That is, it is the square root of the mean of square deviations about the population mean. And based on what we learned in the previous video, that the population mean denoted by mu. And of course, the population standard deviation is represented by sigma. So sigma. Now, based on, of course, the definition looks kind of tedious, and actually we can derive the formula of the population standard deviation based on the definition here. First of all, let's write down the sigma, which is representing the population standard deviation. Now let's get back to the definition here. The population standard deviation is the square root the square root of the sum of square deviations. Square deviations xi minus mu. That's the squared deviations about the population mean divided by the number of observations in the population, capital N. So this is a formula of the population standard deviation based on the definition given up here. And we also have the formula in the slash here. So the sigma is equal to the square root of sum of xi minus mu square over n. So which is exactly the same thing as what we got up here. Of course, the wire x1, x2 through xn are the n observations in the population, and mu is population mean. Okay. And there is a equivalent form of the population standard deviation formula. So a form that is equivalent to the one on the previous slide called the a computational formula for determining the population standard deviation. So in this case, sigma is equal to the square root of sum of xi squared minus the square of sum of xi divided by n, and then the whole thing divided by n. So basically, once we have the formula, actually you can use either one. Either this one or this one gonna work. You get the exactly same answer. They are completely equivalent to each other. So basically, if you have the formula and you have the data set, you can find the population standard deviation by doing the basic calculations. Now let's take a look at the example here. So the following data represent the travel times to work for all 7 employees of a startup web development company. So we got 7 numbers here. Compute the population standard deviation of the data set. So now let's take a look at how we do it. So based on the formula, we have the sigma population standard deviation is equal to the square root of the sum of, this is the sum of xi minus mu squared divided by capital N. Now we have already known that n is 7. So basically, if we can find out each xi minus mu squared and add them all up, basically we can find the answer. Now let's take a look at how we do it. First of all, we list all of the xi here. We get 7 of them here, and the mu would be equal to, mu is equal to sum of xi divided by n, so which is sum of xi divided by 7. Basically, you add them all up, divided by 7, you get the same answer. And actually, I believe we got this number in the previous video as well. And then we want to find out the deviation about the population mean by using xi minus mu, and then we get all of the deviations about the population mean in this column, and we square each of them in this column to find out the squared deviation about the population mean. So this is equal to the square of that, and so forth. So once we got all of the squared deviation about the population mean, we add them all up, got the sum of squared deviations about the population mean. Okay, and then we bring this back into this formula which is the square root of this number 902.8571 divided by 7, and we have this is approximately equal to 11.36. So I wouldn't go over the calculation part by hand in the video, but I'm gonna make a video later to show you how to calculate the population standard deviation and simple standard deviation in the calculator. I'll make a video about that later. Okay, that's pretty much how we calculate the population standard deviation by applying this formula over here. So as we have another equivalent formula, let's take a look at how to apply this formula here. So based on the formula given here, we can tell that if we want to find out the population standard deviation, we have already known n is equal to 7, and we just need to find the sum of all x values and the square root of each x value. and then we just plug them back into this formula. We're done. So we get all of x values, we add them all up to get the sum of all x values, which is 174. And then we have the square of each x value in this column here, and then we add them all up to get 5228, and then we'll plug both of them back into here to find the population standard deviation, which is 11.36, which is exactly same as what we get over here. Okay, so you will also always get the same answer by applying those two formulas, because those two formulas are completely equivalent to each other. So that's pretty much about how to find the population standard deviation. Now, let's take a look at the sample standard deviation. So of course, since we get a word sample here, so this is a statistic. A sample standard deviation little s, denoted by little s, of a variable is the square root of the sum of the square deviations about the sample mean divided by n-1, where n is the sample size. So the difference between the sample mean, sample standard deviation, and the population standard deviation is, number one, we use the sample mean over here. Number two, on the bottom here, instead of n, we use n-1. I wouldn't talk too much about this n-1 over here in this class, because it's beyond the scope of this class. Just remember that if you are looking for a sample standard deviation, you need n-1 on the bottom here. Okay. Of course, where x1, x2, xn are the n observations in the sample, and x bar is the sample mean. Okay. Similarly, a formula that is equivalent to the one on the previous slide, called the computational formula for determining the sample standard deviation, is we have another equivalent form for the sample standard deviation, which is this over here. This is very similar to the one we just saw over here. Okay. Once again, the difference is that we have a -1 on the bottom here. All right, now let's take a look. Let's talk a little bit about a -1 over here. We call a -1 the degrees of freedom, because the first n-1 observations have freedom to be whatever value they wish, but the nth value has no freedom. It must be whatever value forces the sum of deviations about the mean to equal 0. So what does it mean? So that means that if I draw a coordinate over here, okay, I would say, let's see, this is x bar. This is a horizontal line, and we got a bunch of x values. Some of are above x bar, some of them are below x bar. So which means if the point is above x bar, we're gonna have xi minus x bar is positive. If the point is below the x bar, we're gonna have xi, let's say xj minus x bar is negative. So that means the deviations could be positive, could be negative. But if we add them all up, the positive will balance the negative parts. So the sum of the deviations is going to be equal to 0. But why the n-1 is the degrees freedom? Because the first n-1 observations have freedom to be whatever value they wish. But the nth value has no freedom. It must be whatever value forces the sum of the deviations about mean to equal to 0. So just like this, I have 5 pins. I have 5 different pins. Let's say 1, 2, 3, 4, 5. Wait, I have 5 different pins, and I want to give this 5 pins to 5 different students. Okay, and then I have the first student come to pick up pin. Does the student have the freedom to pick up pen? Yes, because the student is gonna have 5 options, right? And then the first student leaves, and the second student come. So this is gone. Does the second student has the freedom to pick up pen? Yes, the person does, because there are 4 pens left. The students get 4 options, and then the second student left, and the third student come. Does the third student have the freedom to pick a pen? Yes, yes. There are 3 pens left. This students got 3 options, right? And then the third student left, the fourth student come. Does the fourth student has the freedom to pick a pen? Yes, there are 2 left. This person get 2 options, and then the 4 students left, and then the 5th student come. Now, does the 5th student have the freedom to pick a pen? No, this person doesn't have a freedom, because there is only 1 pen left. This is for the fifth students, and that's why the degrees freedom is always a -1. Because only the 4 students got the freedom to pick up pen. The last student doesn't have the freedom to pick up pen. Okay. Now, once we know the degrees freedom, let's take a look at the example about how to computing the sample standard deviation. Excuse me. Here are the result of random sample taken from the travel times in minutes to work for all 7 employees of a startup web development company. We get 3 numbers. So basically, if we wanna calculate the sample standard deviation by applying this formula, little s is the sample standard deviation, which is equal to the square root of sum of xi minus x bar squared divided by n-1. So what do we need? We need xi, we need x bar, and then we need the deviations about the simple mean, and then we need the squared deviations about the simple mean. Okay, once we got all of the squared deviations about simple mean, we add them all up and then plug it back into here. We get the result. Now, so we know x bar is equal to sum of xi. Let me get rid of this. Sum of xi divided by 3 in this case. That's how we calculate the simple mean. All right, and then we use the xi minus x bar to get the deviations over here, and then we squared this number to get this number over here, and so forth. Once we get all of the deviations, all of the square deviations about the simple mean, we add them all up to get this number over here. Once we got this number, we'll plug it back into here. Of course, we don't need the square root all the way to the end here. So always keep the idea in your mind. Since we're calculating the sample standard deviation, we need a -1 on the bottom. Since n is 3, so the bottom here is 2. Okay, and then we just plug this number back into here to get the result. That's pretty much how we calculate the sample standard deviation, by applying this formula over here. Since we have a computational formula as well, which is this. So based on the formula given here, if we want to calculate the sample standard deviation, we just need the sum of all xi's, and then we need the square the x values. So we get all of x values down here, and then we add them all up, get the sum of x values, and then we get the squared x values over here. We add them all up to get the sum of the squared x values, and then we plug both of them back into here to get the final result. Okay, and we got the exactly same thing as what we got up here, because those two formulas are completely equivalent to each other. All right, that's pretty much how to calculate the sample standard deviation. Let me say, this part is a design for the face-to-face class, so we skip that over here. Now, once we know the definition of standard deviations, let's get back to the very first example we went over. Determine the standard deviation waiting time for Wendy's and McDonald's, which is larger? Why? So we get the raw data here. So if we want calculate the sample standard deviation, we need to apply the formula S is equal to square root of sum of xi minus x bar over n minus 1. Of course, in this case, n is equal to 31, and we know that n is 30. Sorry. And then x bar, I guess, is 1.39. That was given in the at the beginning of the slide. And then we just need to calculate the sample standard deviation following the exactly same steps we went over here. So I wouldn't go over the calculation part in this video because I'm gonna make a video about how to calculate the sample standard deviation, the population standard deviation from the calculator. Okay, so I wouldn't go over the calculations by hand over here. Now let's take a look at the result directly. Now after the calculation, we got the sample standard deviation for Wendy's is 0.738, and the sample standard deviation for McDonald's is 1.265. So obviously the sample standard deviation for McDonald's is greater than the sample standard deviation for the Wendy's. Recall from earlier that the data is more dispersed for McDonald's, resulting in a larger standard deviation. If we get back to the histograms at the beginning, where is it? It's over here. So we can tell that this histogram here is more dispersed than this graph over here, because this starts at 0, ends at 5, and this starts at 0, ends at 4. And we know the standard deviation of McDonald's, the standard deviation of this, let's say this is S1, the standard deviation of McDonald's is S1, and the standard deviation for the Wendy's is S2, since S1 is greater than S2. Okay? So, the larger dispersion resulting in the larger standard deviation. So we say that standard deviation is a measure of variability. If the standard deviation is bigger, then the graph or the data set is going to be more spread out or is more dispersed. That's pretty much how we calculate and explain the standard deviation. Just once again, if the standard deviation is larger, then the data set is going to be more dispersed. Now, after standard deviation, let's take a look at the variance. The variance of a variable is the square of the standard deviation. So basically, if you want to find out the variance, you got to find out the standard deviation first. And the square of the standard deviation will give the variance. Of course, sigma square, which is the square of the population standard deviation, gave us the population variance, and the square of the sample standard deviation gave us the sample variance. Now let's take a look at the example here. So this is the same example again. So we got 7 numbers here, and we want to find out both the population and sample variance of the data. Okay, so since in the previous slides we already got the population standard deviation and the sample standard deviation. So if we want to find out the population variance, we just need to square this number over here. Sigma squared is going to be equal to the square of 11.36, which will give us 129.05. And similarly, the sample variance is going to be equal to the square of the sample standard deviation. So this is equal to 15.82 squared. Of course, it's approximately, since it is rounded to 2 decimal places. So that's pretty much how to calculate the variance. So the very last part of this section is about the proposition of the standard deviation and sample. So let x1, x2, and xn be a sample, and say be any non-zero constant. If y1 is equal to x1 plus c, y2 is equal to x2 plus c, and until yn is equal to xn plus c, then the variance of y is gonna be equal to the variance of x. Number 2, if y1 is equal to c times x1, y2 is equal to c times x2 until yn is equal to c times xn, then the variance of y is equal to c squared times the variance of x. Okay? And then of course, the standard deviation of y is gonna be equal to the absolute value of c times the standard deviation of x. It's because just in case that the c is negative over here, because we know the standard deviation is always positive. That's why we need the absolute value sign over here to guarantee that this number is positive. Of course, the sx squared is a simple variance of the x, and xy squared is the simple variance of y's. So that's the basic proposition of the standard deviation and the variance. All right, that's pretty much all about this part.